In the next 6 videos, starting from this one, we'll be considering Poisson processes. And in this particular video, our focus is on stochastic counting processes as a foundation for Poisson processes that we'll be looking at. So let's go for that straight up. Um, Starting with the definition of a stochastic counting process. So, we have all kinds of counting processes like that. And since you are looking at stochastic processes in general, it's important to look at stochastic counting processes. So, definition of a stochastic counting process: a stochastic counting process, which is the collection of all n of t for t greater than or equal to 0, is a random process that counts the number of events that occur up to time t. So, and it has the following properties. So, a stochastic counting process is basically a random process that counts the number of events that occur up to a particular time, right? So, the properties are as follows: n of 0 is 0, right? That is the number of events in the beginning is 0, okay? Then n of t is discrete, so you have things like 0, 1, 2, and so on. Then n of t is non-decreasing, so you don't have the numbers keep increasing, they can't be reducing. Then n of t plus s minus n of t is greater than 0. So the difference between any two time steps the difference between a time step apart from any two time steps, in short, is greater than or equal to 0. So the worst it can be is 0. Then the interpretation is this. Examples include numbers of arrivals in a queue. So in the stochastic counting process, you are counting maybe the number of arrivals in a particular queue, number of emails received, and number of failures in a system. So that already gives us a clue into the areas of application of stochastic counting processes. Now, then we talk about increments. Now, the increment of the process over t comma t plus s, that is after some time s from a given time t, the increment is given as n of t plus s minus n of t. This represents the number of events in that interval. So you may be interested in the number of events within a particular interval. Okay, so that talks about the increments. And then we go on to talk about the independent and stationary increments. So independent increments, for instance, counts in disjoint intervals are independent in this case. So, and you have stationary increments such that the difference between n of t plus s and n of t is approximately 9 n of s. So the distribution depends only on the length s, not on t itself. So that is stationary increments. Now, we talk about the Poisson process. So, talking about stochastic counting processes, the Poisson process is one of such processes. So, there are different types of stochastic counting processes, and Poisson process is one of them. So, a process which is the collection of n of t is a Poisson process which rates lambda greater than 0 if n of 0 is 0. That is at in the beginning of the process, right? The number of arrivals or whatever in the system is 0. Then you have independent increments. There are also stationary increments, and then small interval behavior, like the probability that n of h is equal to 1 is equal to lambda h plus small o of h, and then probability that n of h is greater than or equal to 2 is equal to o of h, is of order OH, like that. So, talking about the distribution proper for a Poisson process, n of t is distributed according to Poisson with parameter lambda over time t. So, and with that, we have the probability mass function. P of n of t equals k. So the probability that the number of arrivals in a queue, or the number of emails received, or the number of faults in a system is equal to k at time t is given as lambda t raised power k e raised power minus lambda t over k factorial. And this is a very popular, this is the Poisson distribution that is used for uh, this kind of distribution. So you have inter-arrival times. So since you're talking about counting events happening within a time frame, right? So there's the need to understand inter-arrival times. If we have time 1, time 2, and all that to be inter-arrival times, for a Poisson process, any time of any inter-arrival time ti is exponentially distributed with parameter lambda, and they are independent. All right. So it means since they are independent, the arrival times can then be said to be S of n to be equal to T1 plus T2 plus all of that up to Tn. So this will give us all the arrival times, and the arrival time is distributed. It follows gamma distribution with parameters n and lambda. Then we talk about the variance, mean and variance. The expected value of n of t is lambda t. That's for a stochastic process, right? And then for variance, the variance of n of t is lambda t also. And then we have the memoryless property, which is essentially what Markov chains are about. So for exponential interarrival times, the probability that t is greater than s of s plus t, given t is greater than s, is equal to probability that t is greater than t. So there's memorylessness there, right? So we have an example here. Let lambda be 3 and t is 2. So we want to find probability that n of 2 is 4. So probability that n of 2 is 4, that's at time 2, k is equal to 4. That's what this means, because this is normally probability of n of t equals k. So the solution now, so n of 2 follows Poisson with lambda 6. So in this case now, with lambda t, right, that's 3 times 2, 6 right here. Okay, so that p of n of 2 equals 4 can now be 6 raised to power 4. That's lambda raised to power k, that's 6 raised to power 4, e raised to power minus 6, that's e raised to power minus lambda t, rather, that's e raised to power minus 3 times 2, all over k factorial. So that's 4 factorial. And then, of course, you can always write your Python code to deal with that. So lambda is 3 times 2, k is 4, and then you just write the probability to be lambda t raised to power k plus exponent minus lambda t, that's lambda times t, divided by the factorial of k, which is, and k is 4 here. So that gives you the results you see here. That's 0.133 and all of that. So 4 decimal place, that's like 0.1339. Okay. Now, yeah, so actually this expression, if you punch your calculator for it, you're going to get 0.4339. Well, maybe I can do it in decimals. So you have 6 raised to power 4, e raised to power minus 6, 4 factorial, right? Let's go to decimals to see how that plays out. Okay, so we have 6 raised to power 4, 6 raised to power 4, e raised to power minus 6. So 6 raised to power 4, 6 raised to power 4, 4, then e raised to power minus 6 divided by, okay, no, not this now. So I have to do this. No, this divided by 4 factorial. So that's 0.133, blah, 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 as you can see. So that's exactly what we have right here. That's what this Python code also gives us. So we have example 2. So, what is the probability of no event? That's probability nobody arrives on the queue, no email is received, or there's no damage in the system, depending on whatever you're modeling. So, probability example to probability no events. So that's probability that n of t is equal to 0. That means k is 0. So and that's equal to e raised to power minus lambda t. Because since k is 0, we're supposed to have lambda t raised to power k. And since k is 0, so we have lambda t raised to power 0. So we only have e raised to power minus lambda t all over 0 factorial, because k is 0. So 0 factorial is 1, right? So we only have minus e minus lambda t. So here, if lambda is 5 and t is 1, for instance, probability that n of 1 is equal to 0 is equal to e raised to power minus 5. Of course, we already know that n of 0 is 0. So we have to, use another value, which is not 0 for time. So n of 1 is 0, for instance, will be, that's probability that at the first minute or first second or whatever time step you're using, there's not been an arrival in the system, is e raised to power minus 5. And then, of course, you can compute that e raised to power minus 5. That would be this. You have e raised to power minus 5, and that is 0.000673779, blah, blah, blah. Now, for example 3 now, you want to find probability that time 1, the interarrival time 1 is greater than 2. So since the interarrival time 1 is exponentially distributed, so probability t1 greater than 2 will be e raised to minus 2 lambda. So whatever lambda is now, you can then fix it up and get your results. Then how do you simulate a Poisson process? So we simulate using exponential interarrival times. So here now, it can take a lambda rate 2, maximum time is 10, right? Maybe you want to see people who come within a 10-hour period. So at the 10th hour, or if it is minutes or whatever it is you're considering, then you have for times now, you collect the times starting from time 0, and then if you run that, you end up getting, this kind of thing, and starting from 0 all the way up there. So you have that going all the way to the top. So it keeps climbing. So this gives you the Poisson process sample path. So by time 10, that's you have n of t. About 20 people would have arrived. Then you have the general counting processes. So you have general counting processes. Um, so you have, one of the special cases of counting processes is that Poisson process we just talked about, right? So here now, talking about some other counting processes, you have the renewal process. So interarrival times are arbitrary in a renewal process. So you have T of I, the interarrival times, to be it can follow any kind of distribution. Then you have non-homogeneous Poisson process. So the rate depends on time. That's so in the normal Poisson process, you just have lambda, that's like the arrival rate, as you're going to find out later when we get to Q theory. So, but in a non-homogeneous Poisson process, lambda depends on time. So lambda is not fixed like in the general case. So, but here lambda varies with time. Lambda change arrival rate changes over time. Then in that case, n of t follows Poisson distribution with parameter integral from 0 to t of lambda SDS, like that. So we have an example of time varying rates now. So if lambda of t is 2t, for instance, then the expected value of n of t will be integral from 0 to t of 2sds, which is going to be t squared in that case. Then we have advanced concepts like uh, all this. You can talk about a compensator where this is pi of t. I think this is capital pi or alpha. I'm not sure now. So I think it's pi of t. So no, not pi. It should be omega alpha of t, big alpha, so to speak, of t is integral from 0 to t of lambda SDS. Then you have the martingale. I think we're going to see all of this, especially martingale. I know we're going to see that in a future video. So here, m of t is equal to n of t minus lambda t. So the martingale is the difference between the number of arrivals at time t minus the arrival rate times time. Then you have superposition, which is the sum of Poisson processes. Here, lambda is equal to lambda 1 plus lambda 2. And for thinning, each event kept with probability p. So lambda prime is p lambda. So we can then demonstrate the pinning here. So if lambda rate is 5 and probability is 0.3, probability that the event is going to be kept, then maximum time is 10, and it's starting from time 0. So the number of events over that time. So it keeps changing, because it's random, right? So it keeps changing. So you have the value, it keeps changing like this. All right. So, in summary, we have that a stochastic counting process counts events over time. The Poisson process is the most important example of a stochastic counting process. And that is why this set of videos out will be focused mainly on Poisson processes. So then the key properties, they are independent increment, they are stationary increments, and then interarrival times are exponential. Arrival times follow a gamma distribution, and extensions include renewal processes, non-homogeneous Poisson processes. And then we come to the practice problems. So we have that lambda of 2, let lambda be equal to 2 rather. Find probability that n of 3 is equal to 4. Okay, so lambda is 2. Find probability n of 3 is 4. So if here we're talking about Poisson processes. If lambda is 2, find probability that n of 2 equals 3, right? Find probability that n of lambda is to find probability n of 3 equals 4. Probability n of 3 equals 4. Okay. So here now we have that generally speaking, probability n of t equals k is equal to um lambda t raised to power k e raised to power minus lambda t all over k factorial. That's the Poisson thing we have there. Let me confirm that and be very sure. Yeah, so yeah, right here. Lambda t, yeah, good. So we are good to go then. So with this in place now, we can then have the probability that n of 3 is equal to 4 is equal to lambda. Lambda is 2. So lambda is 2. So we have 2 and time is 3, as you can see. So we know lambda is 2, time is 3, and k is 4. Very important. So we have 2 times 3 raised to power 4 into e raised to power minus e raised to power minus lambda, that is 2 times 3 all over 4 factorial. So that means the probability that n of 3 is equal to 4 is equal to 6 raised to power 4 e raised to power minus 6 all over 4 factorial. So we can get this value from, oh, I think that was all. Oh, that was all we did before. Oh, okay, okay, okay. That's 0.1339. Okay, it's the same issue, same problem. 0.1339. That's what the result is approximated to. So, yeah, so that's done. So, other questions now. So, for T1 greater than 2, we have e raised by minus 2 lambda. So, when we have the lambda, we just do that. Okay, so I've done question 1 now. We have yeah, I mean, with that done, I think we can move on. We know variance is lambda t also, right? That'll be lambda times time. That's 3 times 4, 12. So that works. Then we have all these other ones. Um, Lambda is 2. Probability T2 is greater than 3. So we have that lambda is 2. And we need probability that the interarrival time is greater than 3. So we have such an example. Well, the one I just saw now. This is it right here. So T1 follows exponential distribution. So probability T1 greater than 2 will be e raised to minus 2 lambda. Okay, e raised to minus. So generally, right, we say probability T1 greater than lambda. Uh, Probability T T 2 greater than 3, right? Okay, let me check something because I want to be sure that this 1 and 2 find probability that T1 is greater than 2. So since T1 is exponential, probability T1 greater than 2 is raised to minus 2 lambda. This 2 right here. And then okay, I think it has nothing to do with the particular one. The probability T2 greater than 3 or T2 greater than some particular value, 3, should be e raised to minus 3 lambda, and now that is e raised to minus 3, lambda is 2. So that'll be e raised to minus 6. So we can just get that from decimals, e raised to minus 6. So this is e raised to minus 6. That's 0.0025. 0.0025. That's approximately 0.0025, like that. Okay, so I hand yeah, so you want to look at the rest and take care as necessary. Okay. So let me know how helpful this is for you. So you have questions 1 to 10 here and questions 11 to 20. So just fix up the formulas and get everything. So, but of course, I'm going to talk more about the Poisson processes in subsequent videos. Yeah, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel, let me know. Thank you very much for doing that. If you haven't subscribed, why not go ahead and subscribe right away? Hit the notification bell also so you can always get alerted each time a new video is released. You can also join to become a member of this channel with some special privileges, like getting to see some videos first or seeing some videos exclusively, hanging out with me to discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.